The era of scaling AI capacity simply by manufacturing a faster, isolated silicon chip is now completely over. We have hit strict physical boundaries. Reticle limits cap how large we can make a single piece of silicon, and thermal constraints dictate how closely we can pack them together. The atomic unit of compute has expanded. It is now the entire server rack. This new rack-scale computer is a complex stack. It requires advanced accelerator logic, CoWoS packaging to connect chiplets, stacks of high-bandwidth memory, optical I/O for data transfer, and extreme facility power delivery to run it all. Because the entire rack operates as a single machine, an isolated failure at any one of these layers halts the output of the whole system. You cannot measure a data center's usable AI output by simply counting the GPUs installed. Capacity is governed by a strict multiplicative dependency chain. This funnel illustrates the capacity chain. At the top, capacity is constrained by manufacturing limits, wafer starts, and advanced packaging like CoWoS. Moving down, compute requires scale-out networks, optics, and storage. The final output is gated by power availability, yielding the operated AI outcome. Total sellable capacity is a product of hardware, availability, workload goodput, latency limits, and security boundaries. Because these factors multiply, if any single variable drops to zero, the total capacity of the entire multi-million-dollar rack drops to zero. For example, an undetected optical gray failure, where a laser degrades but does not completely break, or a stalled storage metadata request can leave tens of millions of dollars in GPU capital sitting entirely idle, waiting for data. The true data center bottleneck is no longer silicon procurement. It is the fragile dependency chain required to convert that silicon into finished, reliable workloads. NVIDIA addresses this bottleneck by building a vertically integrated stack. They explicitly co-design CPUs, GPUs, networks, and software to act as one coherent entity. This contrasts the market. On the left, NVIDIA's vendor-centered co-design. In the middle, the open ecosystem. Broadcom, Cisco, and Intel manufacture superior modular components. Connecting these parts with open standards allows communication, but without a shared operational objective, it creates integration debt. To compete, the open hardware ecosystem requires an agnostic, supervisory software layer capable of governing these heterogeneous parts as a single, outcome-aware system. Without unified software coordination, wiring diverse hardware together simply moves the bottleneck from the compute die to the network fabric. The proposed architectural solution is the Predictive Tensor Control Plane, or PTCP, designed as an intelligent software overlay for the open rack. Orchestrating networks introduces a primary engineering hazard. If software attempts to micromanage physics, like nanosecond packet forwarding or laser FEC tuning, it creates control loop conflicts that crash the entire system. This graphic maps a strict boundary layer. PTCP operates in the predictive slow path, correlating cross-domain telemetry to forecast bottlenecks and issue bounded policies. Below, local ASICs, switches, and NICs in the native fast path retain absolute authority over hardware safety. True cluster stability requires strict timescale ownership. The software must predict and guide, while the hardware physics remains authoritative at the nanosecond level. Accurately predicting an AI failure means the system must cross-correlate telemetry from every CPU, every memory module, each optical transceiver, and power supply across the entire cluster. The left side of this diagram illustrates the mathematical challenge. Tracking every possible permutation of job, path, tenant, and device state simultaneously creates an incomputable data explosion known as the curse of dimensionality. If the operational data is too massive to compute in real time, predictive models cannot react fast enough to prevent a hard system stall. PTCP proposes a mathematical solution to this problem, the pattern-of-life tensor train decomposition algorithm. Notice how the algorithm factorizes that exponential multidimensional grid into a highly compressed linear chain of low-rank mathematical cores. This structural compression allows the system to continuously ingest multi-domain telemetry and spot anomalies without having to independently map every single variable. By reducing an exponential data problem into linear mathematics, the cluster gains the ability to forecast its own structural risks before local component alarms are ever triggered. This highly integrated physical rack structure introduces a unique security vulnerability. A single misconfigured agent or compromised identity now has an expanded blast radius across memory, storage, and accelerator planes. Advanced threats navigate these systems laterally. They manipulate authorized pathways to steal model weights or alter configurations without triggering standard endpoint detection alerts. PTCP answers this with topological caging, a defense mechanism that relies on monitoring the mathematical graph structure of the network rather than inspecting data payloads. On the left, we see a vulnerable dependency structure, where an agent has unchecked expanding lateral reach. On the right, the system deploys a signed reachability cage. It severs unauthorized data pathways while strictly preserving the approved workload route shown in green. At the scale of an AI factory, security cannot rely purely on data encryption. It must dynamically manipulate the physical network topology to contain threats while keeping the primary workload alive. PTCP's ultimate purpose is delivering a portable AI quality of service, or AIQoS, outcome contract. This diagram shows how that outcome contract conceptually underpins the entire rack, providing a unified foundation for disparate hardware and software domains. Here we see it serving as a translation layer. It is capable of enforcing a single workload objective across Broadcom Ethernet fabrics, Intel x86 host orchestrators, and diverse accelerator chips. The AIQoS contract dynamically optimizes a complex mathematical mix: job completion time, inference tail latency, recovery loss, and strict energy budgets. In this paradigm, deterministic performance does not mean eliminating all latency. It means guaranteeing that a workload stays within a strictly bounded, predictable operating envelope, eliminating costly tail latency spikes. The PTCP layer transforms a highly complex, heterogeneous collection of hardware components into a single, predictable utility that can be governed by a single intent. The open ecosystem can only compete against proprietary monopolies by proving its architecture works through rigorous, independently validated A/B testing against native baselines. This chart outlines a strict, staged validation pathway, moving safely from initial interface maps and shadow telemetry to production-grade bounded canaries over an 18 to 36-month timeline. The criteria for adoption must be absolute. If this predictive software cannot measurably increase accepted work per watt without introducing instability, the project must be abandoned. But if the math holds, the open ecosystem gains an outcome-aware intelligence coordinating vast arrays of diverse silicon in perfect operational harmony. In the next era of data center scale, the ultimate competitive advantage will not belong to whoever builds the fastest standalone chip. It belongs to whoever masters the mathematical coordination between them.